Okay, now let's look at the discrete perceptron. So far, we have shown that the coefficients of the linear discriminant functions called the weights can be determined based on the a priori information about sets of patterns and their class memberships. That was the case, for example, for the Bayesian classifier. So in this case, we showed that if we are in the feature space or in the input space, and we need to divide these patterns, this one is x1, x2, these patterns, the plus patterns and the minus patterns, using a linear discriminant function, we have the slope and the intercept of this linear discriminant function are called the weight, and we can find them a priori. In what follows, we will begin to examine neural network classifiers, meaning that ways on how to determine the weights during a learning cycle. So we're going to find these weights, the slope and the intercept for the case of a linear discriminant function, using a learning procedure. So the patterns, the sample patterns, so we have x1, x2, xp. So these are vectors. That's why I bolded them, as opposed to these lowercase x1, lowercase x2, which are the components of these vectors. Sorry for any misleading notation. So these vectors, these patterns, they constitute our training sequence or training patterns, and they're fed to the perceptron or to our learning system to find the weights. So let's look at the error correction scheme that we looked at before. So let's say this is our x1, this is our input pattern, the first pattern, x1, x2, xn. So this is x1, this is x2. And then we have a pattern in a multi-dimensional space, so from x1 till xn. And then we're looking, so we're using a perceptron, a TLU called threshold logic unit. So where we multiply x1 by w1 plus x2 by w2 plus xn by plus wn. And then before we saw that we compare this input or this activation to a threshold. Now we move this threshold here and call it wn1, where we add an input xn. And in this case, we have what is called an augmented input pattern. So instead of having just x1 till xn, we have x1 till our input pattern called y would be x1 till xn, and then the last element of that vector would be a 1. And then our activation becomes x1w1 plus x2w2. And then at the end, we're going to add 1 multiplied by wn plus 1. So this will constitute our activation to this neuron, so this threshold logic unit. And then if this activation is greater than a certain threshold, if it's greater than 0 in this case, so it is we say that it belongs to class 1. If it is negative, we say that it belongs to class 2. And this is our output. So our output is a +1 or a -1. Okay, I0 is +1 or -1. And then because we're collecting or working on an error-based correction scheme, so we take this output, O, and then so we look for the error D minus O, okay, D minus O, and then we feed this so we use this error here to adjust our weights. So we're going to see now a geometrical representation or to explain how this weight correction happens. So this is the vector representation in the weight space. Note here that we have We don't have x1 and x2. We're not working or looking at the analysis in the feature space or the input space. This is the weight space. Okay, this is the weight space. This is W1 and W2. And then if we assume that we have 5 prototype patterns, in this case Y1 to Y5. So this is our first pattern, which belongs to class 1. And this is our second pattern, which belongs to class 2. Third pattern belongs to class 2, and so on. So we have the 5 patterns. This is the 5th pattern, which belongs to class 2 as well. And so let's look at the solution space in this case. Okay, so let me just take a pen, a green pen, and then, so if I put my input, my first pattern here, and then I know that, so this is my first pattern, and I know that it belongs to class 1. So the vector, the normal to the hyperplane or to this line here points to to class 1, to the case where W transpose is positive. So because I know that my pattern 1 belongs to class 1, so this is the solution space. So I should eliminate all this, okay? Now when I put my input number 2, my second pattern, input number 2, so I know this is the line, and I know that my pattern 2 belongs to class 2, so this would be the solution space. So I should eliminate all this area here. Now for my pattern 3, I know that it belongs to class 2, so this is the solution, so I should cross this one, so it's not adding any information. And then for pattern number 4, so I know that it belongs to class 1, so the solution is in this area here, so I should cross all this area. Now for pattern number 5, I know that it belongs to class 2, so this is, the solution is in here, so I should eliminate all this area. And that's why this would be my decision, this would be the solution. The solution will reside here. So the weight vector, which is going to allow me to classify correctly a pattern after training, would have to lie in this area here. So of course, if I have the dimension of my input pattern vector is greater than 3, so I will be in a space, in a weight space, which is of higher dimension or more than 3, and I would not be able to look at the geometrical explanation. Now, now let's see how the training happens. Okay, so for example, so there are 2 cases. So the first, assume that this is my initial weight. Okay, and I know that this pattern here, my first training pattern, belongs to class 1. So I am not in the solution space, because when I do W1 times Y1, I will be it would be negative. I would find a negative solution. So I'd be sitting in this area here, but I want to be in this area. So I need to move my weight, my initial weight, so that I fall into this area. And the way to do it is to compute the gradient. So I compute the gradient with respect to W of W transpose Y1. Okay, W transpose Y1. And this would be equal to Y1. So since my Y1 is in class 1, so what I need to do is, according to my learning rule, is the new weight has to be equal to the old weight plus C times Y1. So this is my Y1, this is the vector here. If I choose C equal to 2, so it'll be 1 Y1, 2 Y1. and I will fall in this weight solution area. So I would add a plus here in this case. Now, if in the second case, again, this is my weight space, W1 and W2. And then in this case, I assume that this is my initial weight, and I assume that Y1 belongs to class 2. So this is the weight solution area. And this is my same pattern, W1, but it belongs to class 2 as opposed to class 1 before. So in this case, I would have to, my new weight has to be equal to the old weight minus C. If I say that my C equal to 2, for example, 2 times Y1. So this is Y1. So I need to move 2Y1 to this area here so that I fall into the weight solution area. So it's a correction in the negative gradient direction. Now this is assuming that C is constant. Now let's look at the weight adjustment of 3 augmented training pattern, Y1, Y2, Y3. So in this case, I assume that, so I'm still in my weight space here, and I assume that these are my lines. So this is the pattern number 1, which belongs to class 1. So if my initial weight is here, I need to move a lot because my first training is, my first pattern is Y1 and belongs to class 1. So I should move in this direction along Y1. Now when my input is the second pattern, I should move this weight here. So my new weight should be equal to the old weight plus because pattern 2 belongs to class 1 plus C Y2. So plus C times this Y2 here. So I would be moving in this direction, okay? In the same direction as Y2. Same thing, here I moved in the same direction as Y1 because it belongs to class 1. I moved to the same direction as Y2 because it belongs also, Y2 belongs to class 1. Now, if my pattern Y3 belongs to class 2, so my solution is in here, so I should move in the negative direction of Y3. So Y3 is moving in this direction. I would move in the opposite direction, and I fall in the weight solution area. So the weights in the shaded regions are the solution. And the 3 lines labeled are fixed during training, okay? Now, this was a constant, so C was constant. But let's see now a dynamic way of adjusting this C. So how to select the correction increment based on the dislocates of W1 and the corrected weight vector W. So if, again, this is my decision line, and I assume that my pattern Y1 is in class 1. So this is my initial weight, and I want to make sure that my new weight will fall in the weight solution area. Now, the new weight would be W1 plus or minus C Y transpose Y. And if it is equal to 0, so that means I'm moving my W1 to a point on this line on W transpose Y equals 0. Okay, so I'm moving here on this hyperplane. And from here, because the transpose, so it'll be, I can expand this relationship. So it'd be W1 transpose plus C Y transpose times Y. And then I multiply, so I can find that my C is equal to minus plus W1 transpose Y divided by Y transpose Y. And this is the L2 norm of Y. And then because C is positive, so I can take the absolute value. So this minus plus can be replaced by the absolute value of y1 transpose times y. And because my correction is plus cy, so this cy can be written in this form here. Okay, so this p is a distance. So this p is a distance. This p is the distance to the line. So it has to be positive. Okay, so this is my p, is the distance to the hyperplane. Now, for fixed correction rule where c is constant, the coefficient of the weights is always the same fixed portion of the current training vector, meaning that the new weight is equal to the old weight plus or minus cy. This is my delta W. And this delta W for the case of the TLU or the discrete perceptron is C times the desired output minus the sign times Y transpose, the W transpose Y, which is the activation. And then the delta W is multiplied by Y, okay? Now for a dynamic correction rule, so C depends on the distance from the weight, i.e. the weight vector, to the distance decision surface in the weight space. So it depends on, as we said, this distance here on P. So in this case, the Cy would be equal to the current weight, W1 transpose, times Y, the current input pattern, divided by the norm of the current input pattern, and then multiplied by the current input pattern. Of course, if my initial weight is equal to 0, then Cy would be equal to 0, and there would be no possible adjustment. So the initial weight should be always different from 0. Now let's look at the dynamic correction rule using the value of C from the previous slide as a distance. So we devise an adjustment technique which depends on the length W2 minus W1. So in this case, C equal to lambda times this distance between this is again the distance between my weight and this surface here. So if I put that my C is equal to lambda times that distance, so if lambda is equal to 0, so there's no weight adjustment. If lambda is equal to 1, so that falls. That means that I'm moving to the to fall on the decision boundary. If W is equal, if lambda is equal to 2, so that's a symmetrical reflection with respect to the decision plane. And ideally, I would like to take my lambda between 1 and 2, so that I move not on the hyperplane, but then I fall here on the weight solution area. And I would say I would move in the direction Cy. So if I am here, so I move along this direction of Cyi, okay. Now let's take an example with a single, so y1 equal x1, y2 is because I'm using my augmented input pattern. So the y2 has to be equal to 1. And so my net input or my activation would be W1 x1 plus W2. And this would be fed to a threshold logic unit, meaning it's a sign. So so if it's positive, it's plus O is equal to 1, a plus 1. If the net is negative, that means my O is equal to minus 1. And then this is my desired output. And again, I will look. So if I assume that I have 4 patterns, x1, x2, x3, x4, and then I assume that the odd x1 and x3 belong to class 1, while x2 and x4, the even, belong to class 2. So the desired output for x1 and x3 is 1. For the desired output for x2 and x4 is minus 1. So the augmented input vectors are, so in this case, 1, 1. For y2, it'd be equal to minus 0.51. So all of them have 1. For y3, it'll be 3, 1. For y4, it would be equal to minus 2 and 1. And the decision lines, W transpose yi equals 0. For I equal 1, 2, 3, 4 are sketched on the augmented weight space as follows. So these are my decision boundaries. So this is for the first pattern, the second pattern, the third pattern, and so this is W1, W2. So you can easily find the equations for these lines and then plot them on the weight space, okay? And again, for pattern number 1, I know that it belongs to class 1. So my solution is in this area, okay, for pattern 1. Pattern 2 belongs to class 2, so my solution is in this area. Pattern 3 belongs to class 1, so the solution is in this area, and so on. And then, just like what we've done before, we can show that the weight solution is in this area here. So if I'm starting at W1 here, so because pattern 1 belongs to class 1, so I need to move in the direction of Y1, which is here. So I should move here. For pattern number 2, which is here, so it belongs to class 2, so I should move in the negative direction of Y2. So Y2 is in this direction, I should move in the opposite direction. And now Y3 belongs to class 1, so I should move in the direction of Y3, which is here, shown here. So the new weight, W4, has to be equal to C times that vector Y3. And I'm assuming that my C equal to 1. Now, when I am here for pattern number 4, so pattern number 4 belongs to class 2. So my solution is in here. So I don't have any adjustment. And then you can show that for W4, for all the, so now when you repeat the pattern, so that was for the first epoch when you had your input, you had inputted all the patterns, 1, 2, 3, 4. And then you ended up in a cycle, in a solution where you didn't, sorry, in the case of a weight which does not belong to the weight solution. So you have to repeat the training for another epoch, okay, so that you fall in this area. So for C equal 1, so W1 is equal, so you assume that you have randomly selected your weight, W1, and it is equal to minus 2.5, 1.75 transpose. So you use this training rule where the new weight equal to the old weight plus or minus CY. And so the weight training with each step can be summarized as follows. So the delta W, this delta W is C over 2 times the desired output minus, because you're having a threshold logic unit, sine of W transpose times Y and times the Y here. So let's see how this works for input pattern 1. So my first output here, my first output here would be equal to the sine, because I have a TLU here, sine of W transpose, which is in this case minus 2.75 times 1.75 times my first input pattern. And we've seen that the input pattern in this case for Y1 is 1, 1. So if I do this, so meaning that it's minus 2.5 plus 1.75, you look at the sign and you see that it's negative. So your output, or 1, would be minus 1. And then we know that we know that Y1 belongs to class 1. So D1 has to be equal to 1. So D1 minus O1 would be 1 minus minus 1. So it'd be plus 2. And in this case, I would need to move in the positive direction of the gradient. So my new weight W2 equal to the old weight, which is this one, plus Y1, which is equal to my, which is equal to Y1, okay? 1, 1. Now, if I do the same thing for pattern number 2, so I would have O2 equal to my old weight, so minus 1.5, 2.75, times my second pattern number 2, which is minus 0.51. So I do the multiplication, I take the sign, and this is going to be, so this is going to be positive, so my output 2 would be 1. If I do D2 minus O2, I know that D2 belongs to class 2, so it'd be 1 minus, so it'll be, sorry, minus 1 and then minus 1 because O2 is equal to 1. So I get minus 2 and I need to move in the negative direction of Y2. So W3, the new weight, would be equal to the W2, which is this one. This is the W2 minus 1.5, 2.75 minus Y2, which was minus 0.51. And this is my Y3. And I repeat the same operation for Y3. And I find that this is W4. As I said, there was no evidence that we have correct classification of the weights, W4. So we repeat the training for another cycle or another epoch. And then we get, so my Y4 would be Y1, Y5 would be Y2, and so on. And then I compute the corresponding weights. And I find that there would be no misclassification, so no weight adjustment for this pattern. And then I keep doing the, keep doing it for another epoch and so on until I find that the W11 is in the solution area. And I say that I've reached, or my training has been completed. I've reached the solution, and that's the end of the training.